We present progress on the problem of reconfiguring a 2D arrangement of building material by a cooperative swarm of robots. We have developed two algorithms to a reconfiguration, one based on spatio-temporal planning and the other based on load transferring. Our motivation to solve these problems comes from wanting to increase the number of robots building a structure simultaneously, to make building structures with robots faster and easier. Our previous work looked at the reconfiguration of polyominoes and made obstacles using the RRT star algorithm, but only focused on using a single robot. Our current paper increases the number of robots to m robots instead of just one. Like our previous work, we're using the Billy robot construction system first published by Janet et al. The Billy robot construction system, or Billy bots as we call them, come with their constraints due to design and physical implementation. For example, Billy can only walk on the voxel structure and can only pick up and place one voxel or tile at a time. Tiles must remain connected to ensure that the building material doesn't drift away from each other like it could in different mediums such as underwater or in space. Here's a video showing a Billy bot performing a reconfiguration by himself. His goal is to move all the red tiles from one side of the white cross to the other. This reconfiguration took about 9 minutes to complete. While using multiple robots allows for a decrease in time required to build a structure, it does come with its own challenges like robot coordination, task allocation, and collision avoidance. In order to plan paths for all robots, we implement a decoupled variation of the A-star algorithm. To implement regular A-star, the configuration of the Billy bot is represented as a node. All the configurations that can be reached from said node are its neighbors. Changing the number of valid motions the robot can take increases the neighbors every node has, which can help reach goals faster but becomes more computationally expensive. Two movesets, S5 and S7, are shown here. S5 includes the motions waiting, stepping forward, stepping backward, and stepping forward 45 degrees clockwise and counterclockwise. S7 adds stepping backward 45 degrees. The round foot is the front foot in this graphic. In order to reduce planning times, we decouple the problem by using a temporal implementation of A-star. It relies on a horizon H and priority Q to keep the planning of the robot separate. Every iteration, the next H time steps are planned. Higher priority robots ignore lower priority ones as they move, while the latter try to get out of the way. If a collision takes place during planning, the priority queue is modified by shifting the ID of the lower priority robot up and replanning takes place. We compared our temporal A-star to the regular A-star and a multi-robot version called M-star developed by Wagner and Choset. Although M-star is designed to reduce computational complexity, it still generates a lot of nodes in crowded maps. These animations show several Billy bots moving to different goal positions. The lighter block is the back foot, while the darker block is the front foot. The goal is considered reached if the front foot steps on it and the back foot is in a valid spot. We performed simulations with several maps to compare the planning times for each planner. Different biases for the three planners, as well as different horizon values for temporal A-star, were tested. The X's in the plots indicate the planner could not find a solution within a given time limit. The map with three agents shows that our temporal A-star is prone to looping. However, it does spend considerably less time planning in many cases. Expanding the moveset of the robots, from S5 to S7, also enabled the temporal A-star to solve more cases, as the increase in planning time was overshadowed by the ability to move robots out of deadlocks. Our second algorithm is based on load transferring. This allows one robot to transfer its carried tile to another robot. Transferring building materials between robots helps prevent collision and unnecessary waiting. Due to the design of the Billy bots, tiles cannot be physically exchanged between two robots. Instead, one Billy bot must find a place to drop their tile and then have another Billy come pick it up. Every iteration, the algorithm checks the combined distance cost to the next pickup and drop-off location pairs. A load transfer takes place if it reduces the cost. This happens often in narrow corridors. To avoid increasing planning times too much, only pairs of robots within a certain distance of each other are checked for potential load transferring. The following animations show load transferring in action for different reconfiguration sequences. We tested the impact of load transferring using 8 different maps. These maps were designed with narrow paths. For all but the first map, load transferring decreases their time required for reconfiguration, and the combined number of tiles traveled by the robots. Maps 1 to 4 have 2 robots, while maps 5 to 8 have 3. The temporal A* was used in all cases. Here's a video showing 2 Billybots, Billy Joel and Billie Eilish, performing a load transfer. The goal is to transfer the white tile from one edge of the map to the other. Due to the nature of the map and the number of Billybots, a load transfer is necessary. To differentiate between the 2 Billys, a small flag has been added to the robots with the first letter of their names. This video has also been sped up for time constraints, but the actual build process took around 4 minutes and 30 seconds, which is about the length of the song Piano Man by Billy Joel. For future work, we would like to combine the temporal A* implementation with randomized sampling methods to further resolve deadlocks in complex and crowded maps. We're also interested in extending these algorithms to 3D reconfiguration. Thanks.